3IO Atlas is breaking the rules of physics. When the James Webb Space Telescope locked onto this interstellar visitor, its coma was already expanding faster than any known model predicts. Brightness surged fivefold at a distance where water ice should remain frozen. Dust spread outward in defiance of thermal limits. The numbers refuse to fit. Astronomers admit they have no precedent for what Webb recorded. If Atlas is natural, then we are missing a cornerstone of physics itself. If it isn't, then something built, not born, is moving through our solar system right now, and we may only have one chance to study it before it vanishes back into the dark between stars. Atlas did not announce itself with a dramatic flare. Its first trace came quietly, buried deep in archival frames from the transiting exoplanet survey satellite, a faint streak moving across the star-heavy bulge of Sagittarius. At the time, no alerts went out. Automated pipelines designed to detect periodic stellar dips or obvious moving bodies flagged nothing unusual. The motion was too subtle, the signal too faint, its glow too easily drowned among tens of thousands of background stars. Weeks later, the Atlas survey operating from its Chilean site finally caught what TESS had missed. Its automated sky patrols registered an anomaly, an object brightening sharply against the stellar clutter. This time, the change was strong enough to trigger a human review, and within 24 hours, the Minor Planet Center logged the alert. The MPC's role as the central clearinghouse for small body data meant that almost overnight, observatories across the world turned their mirrors to confirm it. As astronomers scrambled, archival work began. Pre-discovery images surfaced from Pan-STARRS and the Zwicky Transient Facility, each recovery pushing the object's trail farther back in time. Amateurs soon joined the chase, combing through public archives with their own stacking tools, stitching faint traces into the growing record. Only then did the scale of the find become clear. This was not another long-period comet, but a body on a hyperbolic trajectory, crossing into the solar system from interstellar space. Since the dawn of modern astronomy, only two such objects had ever been confirmed. 1I Oumuamua in 2017 and 2I's Borisov in 2019. Atlas was the third, a discovery so improbable it bordered on impossible. Each one a cosmic lottery ticket, each one rewriting the rules. And this new arrival was already refusing to behave. Confirmation brought clarity, but the first light curve raised a harder question no one expected. From its first confirmed measurements, Atlas broke the pattern. Between 636 and 5.46 astronomical units from the Sun, the object's brightness should have risen only modestly. Simple geometry predicts about a 1.5-fold increase as sunlight reflects off its surface and coma. Instead, photometry from Atlas, Pan-STARRS, ZTF, and later JWST shows a surge 5 times greater, and increase so strong that it demanded immediate rechecks of calibration. The cross-checks were meticulous. Observers calibrated flux measurements against field stars of known magnitude, applied synthetic solar analogs, and stacked nightly exposures to suppress noise. Even after corrections for background confusion in the crowded bulge of Sagittarius, the anomaly held steady. Across instruments, across continents, the numbers matched. The light curve rose smoothly, night after night, not as a spike from an outburst or dust fragmenting event, but as a persistent deviation from every established model. To put this into context, comets like Hale-Bopp or 67P Churyumov-Gerasimenko brighten in predictable arcs, their light curves tracing a geometry that can be modeled with simple heliocentric distance. At 6 astronomical units, their activity is negligible, their surface is frozen. Yet Atlas glowed as if it were already within the inner system, reflecting more light than physics allows. The anomaly is not trivial. Solar heating is weak at such distances, too faint to trigger large-scale activity. Volatiles should still be locked in ice. And yet, Atlas radiated with the vigor of a comet already approaching perihelion. With each additional data point, the mystery deepened and the question sharpened. Where is the extra light coming from? If brightness alone strained the models, what came next broke them entirely. Brightness was only half the story. Webb's infrared imaging revealed a coma expanding in size at a rate no physical model could explain. At 6 astronomical units where water ice remains inert, the object's dust cross-section grew from roughly 300 square kilometers in May to more than 1,700 by July, an almost 6-fold increase in just weeks. This was not a transient jet or isolated burst. The expansion was smooth, sustained, and accelerating. Aperture photometry traced the coma's profile, revealing a steady outward push of dust particles on scales far larger than those seen in Oort cloud comets at similar distances. Radial brightness profiles confirmed that the coma was not simply spreading from solar radiation pressure, but was being actively replenished, as though something within Atlas was forcing material outward faster than sublimation models allow. Comparison to Borisov underscores the puzzle. At similar heliocentric distances, Borisov's coma grew gradually, consistent with low-temperature volatiles. Atlas's growth rate, by contrast, resembles an object experiencing perihelion heating, compressed into a zone where the sun's warmth should have almost no effect. Sublimation of water ice cannot explain it, nor can standard models of CO or CO2 activity reproduce the sheer volume of material seen. Every known comet follows a rulebook written by sunlight and chemistry. Activity begins as ice is warm, peaks near perihelion, and fades on the outward leg of the orbit. Atlas was rewriting that script, expanding far too early and far too fast. No known comet physics supports this rate of growth. The implication was unavoidable. Either a new form of natural activity was being witnessed, or something far stranger was at work. Explaining that expansion means facing a simple problem of temperature that refuses to cooperate. At the distance where Atlas was first observed, nearly 6 astronomical units from the Sun, water ice should remain locked in solid form. At those temperatures, below 150 Kelvin, solar heating is far too weak to trigger sublimation. Ordinary comets at this range are little more than inert stones drifting in silence, their activity dormant until they approach the inner solar system. The standard onset of water-driven jets does not begin until around 3 astronomical units, when surface layers warm enough for vapor to break free. And yet, Atlas was already active. Dust and gas streamed outward as though the comet had skipped the thermal threshold entirely. To reconcile this, astronomers turned to alternative volatiles. Carbon monoxide, with a sublimation point near 25 Kelvin, can sublimate even in the outer solar system. Carbon dioxide follows at around 80 Kelvin. Both are known to drive faint activity in some distant comets, hinting that Atlas might carry unusual concentrations of these exotic ices. But the scale of activity stretches even those allowances. The coma was not weak or intermittent. It was vigorous, expanding across thousands of kilometers in a matter of weeks. In solar system comets, such early onset is faint, often barely measurable. Atlas, by contrast, erupted with the intensity of a comet already inside the frost line. To match the observed expansion, Atlas would require volatile reservoirs on a scale never seen before, or a mechanism capable of tapping them efficiently and continuously. If natural, Atlas may be a rare survivor from an alien system, preserving chemistry our comets never carried. If not, the picture is stranger still. A body venting with precision, releasing energy in ways tuned against the cold, would look less like accident and more like intent. When heat cannot answer, chemistry must speak, and Atlas's spectrum does not whisper. When Webb and the Very Large Telescope turned their instruments on Atlas, they uncovered a chemical signature unlike anything in the solar system. Spectral lines of nickel appeared clean and strong, distinct even in crowded star fields. But iron, the element that should accompany nickel in nearly every known environment, was absent. The imbalance was stark. Measurements showed more than 15 nickel atoms for every 1 atom of iron, with some analyses suggesting ratios above 50. For comparison, the Sun's own photosphere contains 18 atoms of iron for every single atom of nickel. No comet has ever displayed this fingerprint. In solar system bodies, iron and nickel are paired, forged together in the explosive cores of supernovae. Meteorites, asteroids, and dusty comets all show them, in near lockstep. Even the most metal-rich comets measured by instruments like Rosetta carried nickel and iron side by side, their emission lines rising together in the ultraviolet and infrared. Atlas breaks that rule. The teams at Paranal Observatory ran every possible check. Instrumental calibration was verified, background subtraction redone, and laboratory wavelength references rerun. Stacked exposures only confirmed the result: nickel without iron. The absence was not buried in noise. It was real. Some theorists have floated natural explanations: selective sublimation of fragile nickel-bearing compounds or unusual fractionation during planetesimal formation. But none convincingly explain why iron would vanish completely while nickel remains abundant. In natural systems, the two are inseparable. In Atlas, they are not. If the data are correct, then Atlas's elemental fingerprint is a signature out of place, a ratio so skewed that it resembles engineered alloys more than cosmic debris. If Atlas is natural, its chemistry challenges the foundations of cometary science. If it isn't, then the spectrum may be more than data. It may be evidence of design. Elemental imbalance is strange, but motion is merciless, and Atlas's path delivers the sharpest test. The contradictions do not end with chemistry. Astrometric fits, charting Atlas's path through the solar system, reveal a motion that is almost perfectly gravitational. Despite a visibly active coma and streams of gas and dust, the object drifts by only about 1 to 1.5 kilometers per day. That figure is vanishingly small compared to what comet physics demands. When comets are active, their jets act like natural thrusters. Every burst of vapor pushes against the nucleus, producing measurable non-gravitational accelerations. Astronomers quantify these effects with coefficients labeled A1, A2, and A3, representing deviations along the comet's orbit. For active comets, these values are never zero. Even modest sublimation pushes the nucleus tens or hundreds of kilometers over the course of weeks. Atlas refuses to comply. Its coefficients hover near the noise floor, indistinguishable from a purely gravitational trajectory. For comparison, 2I Borisov, the last interstellar visitor with a large coma, drifted by nearly 100 kilometers per day as jets of vapor nudged its path. At the other extreme, 1I Oumuamua carried no visible coma at all, yet veered dramatically, accelerating by more than 37,000 kilometers over its solar passage. Atlas stands apart. Its coma is undeniable, stretching across hundreds of thousands of kilometers, yet its orbit remains stubbornly clean, as though immune to the very forces visibly acting on it. Models that combine its observed mass loss, surface brightness, and nucleus size predict accelerations at least an order of magnitude larger than those observed. The numbers are not ambiguous. They are contradictory. If Atlas were a standard comet, its jets would act like rockets, nudging it measurably away from a pure gravitational path. Instead, the measurements show a body resisting those forces almost completely. Atlas is venting gas but moving as though nothing touches it. It is a paradox written directly into its trajectory. If the orbit barely budges, perhaps mass is hiding in plain sight unless the numbers say otherwise. The first explanation astronomers tested was purely natural. If Atlas shows no measurable drift despite streaming visible jets, perhaps the answer lies in its mass. A nucleus so dense, so heavy, that even vigorous outgassing fails to nudge it from its gravitational course. In theory, a mountain of rock and ice on that scale could anchor itself against the push of vapor. But photometry argues against this. The observed brightness, combined with coma measurements, sets limits on the nucleus size. Atlas is large, but not implausibly so. Its reflected light places it well within the range of ordinary cometary bodies. It cannot hide the sheer bulk required to resist jet acceleration completely. This leaves a paradox. If Atlas were too small, its orbit should wander dramatically under the pressure of its own jets. If too large, its brightness should betray an enormous nucleus. Instead, it sits in between, too small to resist, yet too stable to drift. The numbers do not agree with mass alone. A second hypothesis pushes into speculative territory. If Atlas is not holding steady by sheer bulk, perhaps it is maintaining control in another way. The concept is known as active stabilization, an object capable of correcting its own trajectory through directed venting or redirection of thrust. The analogy would be an ion drive or controlled vent, expelling gas not randomly but with intent. Such a mechanism could reconcile the contradictions. Outgassing would still be visible, creating a coma and dust tail, but the net momentum could cancel out, leaving the orbit gravitationally pure. Instead of drifting off course, Atlas would hold steady as if guided. No evidence confirms such control, but the hypothesis resolves the puzzle cleanly. A body that expands in brightness beyond physics, carries a chemical signature unlike any known comet, and resists the push of its own jets fits the profile of something designed, not accidental. Built, not born. Before we entertain intent, we must exhaust nature, beginning with the strangest chemistry we know. A more conservative explanation centers on chemistry. Comets are chemical time capsules, and exotic volatiles could behave in ways unfamiliar to us. Carbon monoxide, cyanogen, and even fragile nickel carbonyl compounds might drive unusual activity far from the sun. These could explain why Atlas glows so brightly at 6 astronomical units, where water ice should remain frozen. In this framework, the nickel lines seen in spectra are not engineered residue, but the product of selective sublimation. Nickel-bearing, Compounds could vaporize at low temperatures, leaving strong signatures without the usual accompaniment of water-driven activity. It is a hypothesis that remains within the bounds of comet science. But even here, the data resist closure. No natural mechanism explains why nickel dominates without iron, its usual partner in cosmic chemistry. Supernova forges them together. Cometary bodies release them together. Only Atlas separates them. The numbers remain lopsided, the signature unbalanced, and the mystery unresolved. To judge the unprecedented, we lean on precedent, and two earlier visitors set the stage. Atlas is not the first interstellar visitor to test the limits of our models. In 2017, astronomers caught sight of 1I Oumuamua, a faint, elongated object sweeping past the sun. It carried no coma, no dust tail, no sign of sublimation. Yet its path shifted measurably with a non-gravitational acceleration that could not be traced to jets. A silent body with invisible forces at work. Just 2 years later, in 2019, 2I Borisov arrived. Unlike Oumuamua, it looked and behaved exactly as a comet should. Its coma and tail shone with cyanogen and carbon signatures. Its orbit shifted in response to outgassing, producing a drift of nearly 100 kilometers per day. Borisov was the textbook case, a reminder that interstellar visitors could obey the rules. Atlas belongs to neither category. It displays a large, visible coma like Borisov, but shows none of the expected drift. Its path remains gravitationally pure, resisting the push of its own outgassing. 3 interstellar bodies, 3 patterns, each one rewriting the playbook. The universe seems to deal its wild cards and contradictions. 3 anomalies, 3 different rulebooks. The James Webb Space Telescope has become the decisive instrument in this mystery. With its infrared sensitivity, Webb can detect volatiles long before they are visible in optical light. It reads the faint heat signatures of carbon monoxide, carbon dioxide, and nickel-bearing compounds that would otherwise remain invisible. Compared with Hubble, Webb extends the reach into early activity zones where traditional comets should still be inert. Its mirrors can separate faint objects from the crowded star fields that often bury signals. Without Webb's ability to capture spectra at 6 astronomical units, Atlas's rapid expansion might have been dismissed as a calibration artifact, written off as noise. Instead, Webb revealed a growing coma and a spectral fingerprint unlike any comet in the solar system. By catching the object in its early, unexpected phase of activity, Webb turned Atlas from a faint-moving speck into a full-fledged anomaly. Powerful as Webb is, one mirror is not enough, so a global net tightens around Atlas. Once Atlas's unusual behavior was confirmed, the observing campaign widened into a global effort. The Atlas network, with stations in Hawaii and Chile, tracked nightly light curves. Pan-stars contributed deep wide-field imaging. The Rubin Observatory, preparing its legacy survey of space and time, added cadence sweeps to refine the orbit. Amateur astronomers joined in, combing through public archives and recovering pre-discovery images. Citizen science groups used Discord servers and Telegram networks to coordinate, stacking exposures and reporting flux changes in near real time. Each frame filled a gap, building a timeline too fine-grained for any single survey. Every night matters. The next spectral anomaly, the next sudden brightening, the next unexplained stall and drift could appear without warning. Professionals and amateurs alike are watching, feeding data into the shared models. With Atlas, discovery has become distributed. A global network is chasing an object whose behavior challenges everything we thought we knew. Every night counts. As Atlas draws closer to the sun, another challenge emerges: the blackout window. During solar conjunction, when Earth and the object align on opposite sides of the sun, observations become nearly impossible. Instruments are blinded by glare, spacecraft are forced to pause tracking, and data streams go silent. This is not without precedent. The SOHO spacecraft has watched hundreds of comets vanish as they skim the solar corona, lost in brightness and plasma storms. Some fragment, some survive, but during those crucial hours or days, we see nothing. For Atlas, the stakes are sharper. If another impossible maneuver occurs during blackout, no telescope will catch it. The event could pass unseen, leaving only the before and after trail for astronomers to debate. The most decisive clue in this unfolding mystery might emerge at the very moment we are blind. The arrival of Atlas is not just another entry in a database. It is the third confirmed interstellar visitor in less than a decade, a sequence of discoveries with vanishingly small odds. Either the universe is sending more travelers our way, or our instruments have only just become sharp enough to catch them. In either case, the implications are profound. SETI has long focused on listening, radio beacons, laser pulses, whispers in the cosmic noise. But Atlas reminds us that not every signal is a transmission. A macroscopic technosignature could arrive as an object, silent but enduring, crossing the gulf between stars. Built, not born. If these visitors are purely natural, they still stretch our physics and chemistry to their limits. If not, they may be evidence of intent, artifacts adrift, messages without words. Either possibility forces us to rethink our place in the cosmos. Atlas defies the models. It brightens fivefold at 6 astronomical units, where water ice should be frozen. Its coma expands from 300 to 1,700 square kilometers at a rate no comet physics can explain. Its spectrum carries nickel without iron, a chemical imbalance never seen before. And through it all, its orbit remains gravitationally pure, resisting the drift that visible jets should impose. 3 explanations stand before us. Hidden mass, a natural solution that collapses under photometry. Active stabilization, a speculative but clean resolution that hints at engineering. Exotic chemistry, plausible yet incomplete, unable to explain the missing iron. None are definitive. All leave questions open. The call is simple. Keep eyes on the sky. Every spectrum, every image, every anomaly matters. Atlas will not pass this way again. We have one chance to gather its story before it fades into the deep. If Atlas expands beyond physics, then perhaps physics is not the limit after all.